So yesterday we started the point 3 of the second lecture, which was called existence of compatible and tame structures. Our framework is a real manifold X of even dimension together with nowhere degenerate exterior two form, meaning that omega to the power n never vanishes. At this point, we do not require that this form is closed. Recall that an almost complex structure J is called omega compatible or calibrated if two conditions are satisfied. First condition is that omega of Ju Jv is equal to omega of uv for all tangent vectors u and v. And second condition is that omega of u Ju is strictly positive for any vector which is non-zero. This allows us to define a Riemannian metric on our manifold, just putting g of uv equal to the omega. And moreover, we can define a Hermitian metric, putting it equal to this Riemannian minus I omega uv. So it just, you read the decomposition of the Hermitian metric in the reverse direction. And finally, J is called omega tamed if only the second condition is required, positivity for non-zero u. Well, and then again you can construct a Riemannian and Hermitian metric. You need only this. So our first statement on this set of results was announced yesterday, proposition 1. Let J be a omega compatible almost complex structure on an open set U in X. Then for any relatively compact U1, there exists J1, an almost complex structure on the whole of X, also omega compatible, such that it extends our structure J. J1 restricted to U1 is equal to J. So this gives you a flexibility. You can extend structures from open set to the whole space. Well, and in particular, you have always, for any non-degenerate form, you are ensured that you have almost complex structures which are compatible with this form. Proof. Well, so we take a Riemannian metric which is defined by our form. So on U, this exists on U. Then using partition of unity, we can extend the restriction of U onto a relatively compact U1 to a Riemannian metric J1 on the hollow X. Well, and now we shall play backwards. From J1 we shall construct a structure. So by Riesz representation theorem, there exists a unique operator A1 in tangent spaces. Well, all considerations will be from linear algebra at one point, in fact, such that omega uv is equal to J1 of A1 of u v. Okay. So we have a scalar product, and if we fix v, we have a linear form on u which is non-degenerate. So there is a unique vector which corresponds to this u. This is A1 of u. Now, since omega is antisymmetric, this immediately implies that A1 is antisymmetric itself. J1 of A1 of u v is equal to minus J1 of u A1 of v. That means that A1 transposed is minus A1. So it's antisymmetric linear operator. And therefore, A1 T A1 is equal to minus A1 square. And it is a positive operator, self-adjoint, positive self-adjoint operator. Let Q1 be a positive square root of it. Claim if I set J1 equal to A1 times Q1 minus 1, then this is an almost complex structure. Almost complex structure. Well, proof is simple. J1 square is A1 square Q1 minus 2, and this is equal to what? Q1 minus 2 is A1 minus 2, A1 square with minus, this is minus identity. Second claim is that on U1, one has that J1 is equal to J. So why is that? So let us write this. Omega of J of u, J of v. We know that this is equal to omega of uv because our structure is compatible. This is, by definition of A1, J of A1 uv. Not J1, but J, because on U1 J coincides with J1. Okay. G coincides with G1. Now, and this is omega, again, A1 U JV. So we got that J of U is equal to A of U for all U's. So we obtain that J1 is equal to is equal to A1 on U1. Therefore, Q1 is minus square root of this guy to the square, which is identity. So on U1, Q is identity. And therefore, J1 is equal to A1 on U1 is equal to J. Exercise. Check that J1 is omega calibrated. Well, do the same type of computations and check it that it is omega calibrated. Now, an important remark from the proof is the following. So, inside of the proof, we did the following thing. We constructed a mapping from the space of metrics to the space of structures. Namely, given a metric, J1, we produced a structure. Moreover, we proved that if our metric comes from structure, if our metric is coming from structure in this way, then P of G is J. P of G is J. This was checked here. Now I'm going to use this mapping to prove the following corollary. Yeah, this is proposition 1. This is important because tomorrow I will refer to these propositions. Let x omega be as in proposition 1, then first the space of omega compatible almost complex structure, which I will denote from this time as G, so J omega compatible. The space of compatible complex structure is not empty. Well, there will be only one statement, I'm sorry. Then this space is non-empty and is contractible. So it's a non-empty space which is contractible to a point. Proof. Well, so if in our proposition we take U to be an empty set, then we just take any metric and produce a structure, as we did. Okay, so the first statement is obvious. Well, then, for any metric, metric, we produced a structure. Now denote by C the space of metrics. Of Riemannian matrix. This is a cone. This is a cone in the linear space of homomorphisms from Tx to T star x. Yes, every metric is a homomorphism from the vector space to its dual. And it is a cone of positive elements. So it's something like that in infinite dimensional space. Therefore, this thing is contractible. So you can fix some metric J0, fix some metric J0, which will be convenient for me to take in the form omega u of J0V for some J0 in my space of compatible structures. And then there exists a contraction map, so there exists a continuous map. There is a continuous map psi from this cone times unit interval to itself, such that it is a contraction. That means that psi at time 0 is identity map, and psi at time 1 is a constant map to the metric I choose. So I can contract this thing to a point. And now I had a map I have one more map, phi, from the space of structures to the space of matrix, which goes as follows. J goes to the metric omega u jv. Now, and I have this map which I indicated here, and I have a map P from the space of matrix to the space of structures, which was constructed in the proof, and which has the following thing, that P such that P composition with phi is identity as the map from structures to itself. So now what I need to do, I take composition P with construction and with phi. So phi will send complex structures to matrix. This guy will contract them to the point, and this guy will send them back. And this will be a contraction of the space of structures to this structure which was chosen at the beginning. Yes, so we reduce the question of existence of structures to matrix, and also we deduce some important property of the space of structures. So it is contractible space, And this goes from the fact that the space of matrix is contractible. Well, the same can be proved for tamed structures. So let me state this as proposition 2. Proposition 2. Let x omega be as in proposition 1, and let j omega without c denote the space of omega tamed structures, be the space of omega tamed structures. Then G omega is not empty and contractible. Second, for any u in X and any relatively compact u1 in U, and any j on U, omega tamed, there exist j1 omega tamed on the whole of X such that j1 restricted to u1 is equal to j. Well, proof is very the same, in the same spirit. Okay, now I will need one more proposition of that kind for the future. So let me recall the following thing. Let M1 and M2 be real surfaces oriented in the unit ball in R4 such that M1 transversally intersects M2 at 0. So suppose they have one intersection point, and intersection is transversal. Well, smooth. I forgot to tell this. So you have two smooth surfaces inside of the unit ball intersecting at one point, and intersection is transversal. You take a base V1 W1 of basis of the tangent space to M1 at 0, positively oriented, so which gives you in this order the orientation of the tangent plane, and the same for M2. So positive basis and positive basis of T0 and 2. Okay. So if the following basis of R4 is positive, gives you the orientation, the canonical orientation R4, then we say that the index of intersection of M1 and M2 is equal to 1. If this thing is negative, then we say that intersection index of M1, M2 is minus 1. Proposition. Yes, I'm sorry. One more definition. So let U from S to X omega be an immersion of a Riemann surface S to X. This immersion U is called omega positive if the pullback of the two form omega never vanishes on S. If omega is symplectic, in addition, if omega is closed, such immersions are called symplectic. Well, omega symplectic. But we still do not suppose that our form is closed. Well, now proposition. Let M be U of S be a omega positive compact, my positive immersed compact surface in X omega without boundary. Suppose that M has only positive transversal self-intersections. Then let omega, let J be some omega compatible or tamed almost complex structure on X. Given a neighborhood U of M, there exists a relatively compact neighborhood of M, which is a relatively compact subset of U, and a continuous family, JT, T rounds in the interval 0, 1, a continuous family of omega compatible or tamed almost complex structures such that A J0 is our J. Second, for every T in 0, 1, the set of X where JT is different from J is contained in U1. So this family is a perturbation of structures inside of any given neighborhood. C, M is J1 complex. So you start with any structure, you perturb it inside of small neighborhood of N, and you arrive at the end with a structure which makes your surface complex. D, well, and of course, all JT are, this I already wrote. Well, once more. No. So I just wanted to say that they are all omega compatible, but I had put this into the statement. So no D. Well, proof. Proof is somehow, well, it uses, of course, proposition 1. And a little bit more than proposition 1. Well, denote by J bold the set of orthogonal complex structures on R4. So J belongs to this set if JT is equal to J minus 1, which is minus J, of course, because of this structure. Well, and of course, J square is minus 1. So this is a set of special matrices. And, well, the following thing I'm stating as an exercise. The elements of this set are of the form we denote them by Js, where S is a parameter. 0 minus S, S0. The same is here. So 0 minus S, S0. And here C1, C2, C2 minus C1, and minus C1 minus C2 minus C2, C1. So C1, C2, S are arbitrary real numbers satisfying this condition. And moreover, Js, so the standard symplectic structure in R4 evaluated on X, Js of X, is S time norm x squared. So in particular, this structure is omega tamed if and only if S is positive. So in particular, Js is omega tamed if and only if S is positive. Therefore, the space of orthogonal structures is a sphere in R3, and those who are compatible is an upper semisphere. Yes? Hmm? C1 of the tangent bundle with respect to the structure J. So this is a complex but not line bundle. This is a complex vector bundle. And C1 of a complex vector bundle is defined as C1, the exterior power. So if dimension was n, so exterior power to the power n of Tx. This is the line bundle. And this is called the Chern class of our almost complex manifold Xj. Chern class depends on the complex structure in principle. But now, since J belongs to a contractible set of structures, then you can move any J1 to any J2 continuously. And C1 will also vary continuously, but belonging to a discrete group. So it will not change at all. So this thing does not depend on J. So it's constant on the space of structures. And therefore, this thing is said to be the first Chern class of X relative to the form omega. If omega is clear from the context, you just write C1 of X. So the first remark is that Chern class of a almost complex manifold does not depend on the complex structure. It depends only on the exterior form. Second, well, I already gave a definition of a Chern class of bundles of higher rank. Now, if bundle E is a sum of two bundles, or more generally, if we have an exact sequence E1, E, and factor is E2, then the Chern class of E is equal to the sum, Chern class of E1 plus Chern class of E2. And third, geometric interpretation, if X is a complex curve and L over X is a complex bundle, I don't need holomorphic structure on the bundle. Well, it always exists, compatible with complex, but at this point I don't need. Then the first Chern class of L, now this is a cohomology class. Cohomology class you can integrate over two-dimensional. Second cohomology class is represented by a two form. you can integrate it along two-dimensional manifold, which is our case, and this will be a Chen number. Chen number. So it's integral over x of C1 of L. And this has the following geometric interpretation. It's an algebraic number of zeros of a generic section. No, smooth, of course, generic smooth section of U of L. So you have a line bundle over a Riemann surface. So what is its Chen class? You take a generic section and you compute the number of zeros with signs. If this graph here is like a complex graph, then sign is +1. If it's like an anti-holomorphic graph, then sign is -1. Well, I could recommend this as an exercise. Just write functions which vanish with this order, look, and they overlap by transition functions of the bundle, and then produce these deltas. Well, it's quite handleable. Okay, so this was about Chen classes. I hope I don't need anything more about them. And now I'm approaching to the genus formula for symplectic surfaces. Now, one more thing I am required to say. Now, again, if I have two surfaces, M1 and 2, in the unit ball in R4, two oriented surfaces. Now, I don't suppose anything, well, I suppose only one thing, that the boundary of Mi is just intersection with the boundary of the ball. So they go nicely up to the boundary. And they are disjoint. M1 does not intersect M2. Otherwise, I don't suppose anything on how they intersect. Then, how to define the intersection index of these two things? You make a perturbation, smooth perturbation of M1, M2, and make them intersect transversely at all points. And then the sum of indices of these perturbations counted by points where they do intersect is the intersection index of M1, M2. It does not depend on the perturbations, and this is a theorem, is the linking number of the curves delta M1, delta 2, M2 on the three-dimensional sphere. So it's a topological invariant which can be correctly assigned to any two smooth surfaces. This is the first thing. Second thing, if I have a compact surface in four-dimensional manifold, everything oriented, then it defines me a class in the second homology group of X with integer coefficients. The self-intersection of this homology class is the following thing. You take M and you take its perturbation in such a way that they intersect transversally. And this is the index of their intersection. Well, maybe it's not a definition of the homological self-intersection, but it is how it can be computed. And now, theorem, which is a genus or a junction formula. Let M equal to the union of M k, k from 1 to d, be a compact omega positive immersed well, of course, oriented surface. But if it's omega positive, it's automatically oriented surface in a 4-dimensional manifold X equipped with nowhere degenerate form, nowhere degenerate form omega. So our standard setting for today. Let we have an immersed omega positive surface. It can have any intersections. Self-intersections, mutual intersections, no transversal, positive, negative, everything you want. The only thing is that it consists from d irreducible components, M1, Md. Then the sum of genuses jk, k from 1 to d, of mk is equal to the homological self-intersection of M minus C1 of x evaluated on M divided by 2 plus number d minus delta where delta is a sum, well, is a sum of indices of local intersection indices of M. So you took all points of intersections and you compute the sum of intersections. What? Where delta is the sum of local intersection indices of M. I start from this now. So proof so let us start from what is delta. We have M. So it's M1, it's M2. Now what we do, we perturb all components in such a way that mutual intersections and self-intersections become transverse. This is what we do first of all. And then delta, so at each point we have an intersection number plus or minus 1. And our delta is the sum of delta at PL, where PL is a set of self-intersection points. And these are plus or minus 1s. Okay? Now it's clear what is delta. Yeah, so you perturb, you make everything to intersect transversal, and you compute indices. Now, let us take, well, as we already did, let us take to every mk I take a normal bundle, and I consider mk or m tilde k after moving as a zero section in a normal bundle. Okay, so as a zero section. Now I can find a neighborhood Vk of mk in the normal bundle, and I can lift omega to this neighborhood, and I'm not going to change the letter for omega. And what I can find an omega compatible almost complex structure Jk on Vk, such that Mk tilde is Jk complex. This can be done by our proposition 3. Finally, now since our manifold Mk is complex now, because Jk restricted to Mk is a complex structure on Mk, so this object is a Riemann surface, is a complex curve. And as I explained at some point, I can parameterize, I can find a map UK from this complex curve to Vk, which is Jk holomorphic, embedding, and its image is my surface Mk. Now I have the following exact sequence. The tangent bundle to Sk by the differential of UK, which is complex linear, I can map to the following bundle, Ek. This is a pullback by UK of the tangent bundle to Vk, which is equipped with the structure Jk. So I pull back the tangent bundle. This is a complex, two-dimensional complex vector bundle. I pull back on S, and I got a two-dimensional bundle, and my differential is a natural map between these two complex bundles. And this differential never vanishes because UK is embedding. So it's an injective map, which means that here I have a 0. And since it is of dimension 1, this is of dimension 2, the quotient which I shall call a normal bundle, is of dimension 1. Now, geometric sense of this. We have a Riemann surface, Sk. We have a map, Uk. We got a embedded curve, Jk complex, in some neighborhood. And the image under this differential of the tangent bundle is a tangent bundle to this curve, and N is a normal bundle. Well, what is left is to compute our invariance, where is my, Now, all what is left is to compute our numerical invariance from this data which we have here. Well, so now from this exact sequence, we see that the first-chain class of the bundle Ek is the sum of the first-chain class of the tangent bundle to our Riemann surface Sk plus C1 of Nk. So now integrating over Sk, I will have numbers here over Sk. And this is the value of the first-chain class of our surface on Mk. Now here we'll have the first-chain class on the tangent bundle integrated over Sk. This is the Euler characteristic of the surface Sk, which is equal to the 2 minus 2jk, plus chain class of the normal bundle evaluated on Sk. As I explained you, it is a number of sections of the zero of the generic section of a normal bundle, and number of zero of generic section of the normal bundle is the same thing as you take your Mk per tube and compute intersection. So it's a self-intersection number, delta k. So how Mk intersects with its perturbation. So already this is perturbed, so I must write something like that. So you take M tilde k, you perturb it, you compute this intersection, and this will be C1. So summing up, we got the following formula. Summing up, we got the following formula. Sum of C1 of x on Mk, k from 1 to d, which is, of course, C1 of x on M, is equal to 2d minus 2 times sum of genuses plus sum of intersections, self-intersections of Mk. So this is a sum of homological self-intersections of Mk. as I explained you what is a homological center extension. So therefore, we got that D, no, what? No, we need sum of the genuses. Sum of the genuses is equal this minus, so sum of homological self-intersections minus first chain on M divided by 2 plus D and minus local intersection indices. Well, okay, I was not very accurate here. Here is a point that MK has self-intersections. So it is not really a homological self-intersection, but a homological self-intersection minus double sum of points where MK intersects itself. So better I erase this. I just write this is homological self-intersection minus sum of self-intersection points. So this is also not the sum. Okay, so once more, once more. So I have this number, which is intersection of AK with its perturbation. Now, what is that? If you have an immersed surface, then if you move it, each point of self-intersection will produce, if you move it, will produce you 2 points of intersections, which you must subtract. Okay, so, and then you divide by 2, so you get this. Now, it's already almost our formula. Only one thing it should be taken into account is that this sum so I think I lost myself because so let's go to the beginning. So what we have here, we have this formula, then this formula. This is a chain class of those. This is an intersection upstairs in the normal bundle of MK with its perturbation. Now, and so I can write it here. So from here I got the sum minus chain plus D minus now, and what is this? Now, if you look downstairs, so this here you have embedded curve, downstairs you have immersed curve. Now, if you move this and compute self-intersection, then what you get here? If you move this, you get more self-intersections. You get this self-intersection plus double points. So therefore, the homological thing will be M squared minus 2 times delta K. Yes, so it's okay. Okay, and this is our formula. No, so this is just topology. Well, and so what? So my time is over. Okay. So we arrived to a junction formula for symplectic surfaces, and we shall need such formula for arbitrary pseudoholomorphic curves. Okay, this will be done next time. I'm sorry, Sasha. That's all.